Hi, my name's Rob Patterson, and I'd like to welcome you to today's Tech Talk, which is being parallel in a serial world. So let's start off by saying what this presentation isn't. It's not a deep dive into .NET techniques for concurrent execution. If you're interested in that, I've got another presentation called Task Me where we get into the nitty-gritty details of how this works, and quite frankly, it's kind of cool. So what is this presentation? Well, this is a talk on how we successfully use the Task Parallel library to make a simple but powerful speed enhancement to our application. And really, this is about simple stuff. Done right pays off nicely. And I'm going to say this a couple times, so here's the first time. I want to encourage everyone to focus on optimizing bottlenecks. Avoid changing areas that don't pay off. It is pretty easy to get yourself spending a lot of time doing dangerous stuff in an area that you don't want to touch. So just think about it. So, what issue is being addressed? Well, we have an application that computes something called a hook load plot. And it's often useful to take a look at different hook load plots over a range of different friction factors. So, we're basically running the same calculation with different data sets. We're looking at a range of friction factors. And when we do this, it can take a while. Now, this is a great candidate for a multi-core optimization, something where we're doing something very similar and just looking at different data. So let's continue on. So let's do a before and after. And to do that, one of the things that's useful is to actually see the CPU performance chart. So we'll start up the performance monitor. And here's the before picture. So I've got my 4-core machine. And I run this hook load. And this actually took 56 seconds to process 2 ranges. That's a total of 9 combinations. If you're wondering where the 9 comes from, it's a range of 3. It's top, middle, bottom. So we took 2 things, 2 different friction factors, and I said, okay, this one I want to range over these 3, and this one I want to range over these 3, and I want to see all the permutations and combinations. So that's a total of 9 recalculations of this hook load plot. If we take a look at my CPU graph, you can see that this is a very CPU intensive operation on 1 core. I've basically pegged a single core. It's just grinding, it's doing calculations. This is something that, we could do better. So let's take a look at the end result of this exercise. And here, this is the after picture. We get identical results. You'll notice that actually was a before and after. Those weren't the same screenshot. That's the same thing. You get the same results. And over on the side, we can see the CPU chart, which looks a lot different. So this was on my 4-core machine, and I was able to reduce that 56 seconds to 19 seconds. Same thing, we're processing, those 2 ranges, so that's a total of 9 calculations being run. And as you can see, the CPU utilization shoots right up to the top, stays there, and then it's done. And in case you're wondering, the application actually never became non-responsive. Okay, the fact that it was able to use all of my CPUs, that's a good thing, but it didn't lock up the event dispatch thread unnecessarily. So it was still responsive. It's quite a nice thing when you do this thing correctly. Let's talk about what this thing is. So how did we achieve this miracle? Well, it's pretty obvious stuff, actually. We use the Task Parallel library to allow the multiple calculations to execute in parallel. So you say to yourself, hey, this should be easy. It should only take, a minute or 2. Was Rob goofing off the rest of the iteration? Well, maybe, but that's not relevant. No, it's not relevant. There was lots of work building up to the point where we could use parallel.forEach. That's the relevant thing. So what was this work? Well, when you think about the problem, it kind of becomes obvious. There's stuff that we do that can't be parallelizable, that shouldn't be parallelizable. Prime example of that is anytime we interact with the event dispatch thread. Any code where we're doing that, one thread to rule them all, your UI thread. So yeah, that's pretty obvious. You got to do all of your UI code in the UI thread. Also, if there are any dependencies between the different things that we're running, then you would need to do the appropriate work there too. So in this case, what did these constraints mean to us? Well, actually there's some good news. Let's take a look at what we're doing here. The hook load plot uses something called the drag chart calculation. And the first thing I had to do was take a close look into the drag chart calculation and make sure that it's stateless, which is a very good thing. And it turns out it is. So this drag chart calculation is a piece of code where we pass all of the inputs and we pass it to this calculation and we basically say, please chew on this and give us the results back. This is a great example of functional code. You pass all the inputs and you'll always get back the exact same output. And that's what we have here. Even though this drag chart calculation is very old, it was well designed, and because of that, it was relatively easy for us to parallelize it. So, what did these constraints mean to us? I'm talking about, the UI threads and stuff like that. Well, basically there's some work we need to do before the calculation and some work after the calculation that isn't necessarily parallelizable. So before the calculation, we need to build data structures. What are those 9 calculations that we need to run? Let's build the data structures for those 9 calculations. And believe it or not, some of that code is, interacting with the UI. Find me the current setting for this. Find me the current setting for that. So I could have tried to parallelize that code, but it didn't make a lot of sense. And the reason why it didn't make a lot of sense is that if we put this under the microscope, we find that 90% of the time is spent in the calculation. It's not spent in that before and after phase. The before phase is all about gathering the inputs, creating the data structures so that we creating the data structures for the calculations. And the after phase is all about, updating the graphics. And so I went with what I call the smart and safe approach, which is to leave the before and after phases executing single-threaded. So we just leave that stuff alone, and we parallelize the important stuff. So that leads us to our general design, our abstraction, which was sequentially build all the calculation input data structures. So when we talk about refactoring the code, we just, same as it ever was, we sequentially build all those calculation input data structures. Then, when it comes time for the calculations to execute, we're able to, go parallel. We're able to say, hey, all you calculations, please run these. And it's nice stuff. And then when we're done, when all the calculations are complete, we publish the results by sequentially processing those output data structures. I gave this design a name, so let's just don't worry about that. Now, always good to look for abstractions, and so you have to ask yourself, is there a nice reusable abstract design we can handle calculations in this way? And the answer was absolutely, and this is key, and we can take a look at that in a minute. In this particular case, there's a chunk of code called range helper. It's this static class, and that's what's used for, remember I said there's 2 ranges of friction factors. The range helper class is the guy that says, please run this calculation multiple times. And so this is the place where we need to make little changes. So the first thing we should ask ourselves is, can we change the range helper code to use our new design for all calculations? I'm a believer, yeah. I was going to say I'm a believer in, keeping things dry. But in this case, well, there's quite a bit of work involved in actually changing these calculations so that they can be parallelized. And we have a lot of different calculations, so I decided to leave the existing range helper alone and create a different range helper to work with parallel code. And so that's what we ended up doing. So that's what I did. So time to refactor. This is one of those cases where refactoring actually pays off. Refactoring isn't always a good thing, I'm a believer in, don't change it if it ain't broken. This is a case of we want to take existing code and we want to change it in a way so that it will be easily parallelizable. And that's a great refactoring exercise. So the first refactor was I took that range helper and I copied it into a class called range runner. Okay, and I had to make it non-static so that each calculation has its own range runner. No rocket surgery there. In case you're interested in the details, the range runner exposes iRange interface that the calling code calls. Also, I took our range helper tests and I created a test range runner class. As a matter of fact, I don't even think there was range helper tests. I think I had to create this stuff fresh. So yeah, always test, test, test. After the refactor, we're able to change the range runner to use the range runner that the calculations use. Does that make sense? So before the refactor, everyone's using the range runner. And after the refactor, we're able to change them to use range runner. Hope I said that right. So moving forward, going parallel. Next, it was time to create a class called Parallel Range Runner. So Parallel Range Runner started out as a copy of the Range Runner class, right? Then, I add some tests. Let's do some tests. And you may ask yourself, and this is a good question, how do you test parallel code? Well, just remember this. You're testing the code. You're not testing the parallelism. Okay? The task parallel library was, that they've got unit tests for testing parallelism. You just want to test the unit of execution. So if you focus on that philosophy, you can write good tests, and that's what we did here. So there's a nice test for testing the parallel range runner. And then we add some new unit tests for stuff that was only supported when we did the parallel range runner. And then finally, once all this refactoring's done and the tests were run, it was simply a matter of changing this one thing so that we would use the parallel range runner. Now, I've always got to be honest. I'd like to say it was simple as flipping the switch, but really it was more like flipping the switch and then realizing that I got something wrong and debugging it. But to be honest, it only took like an hour to figure out what the heck I screwed up. Once I threw it under the debugger and did a little debugging, flipping the switch, it was like magic. So those tests helped me get it right very close to the first time. And here we're just looking at some stuff. What did we need to change in the calculation for the parallel range runner? So let's just wrap this up. What did I learn out of all of this? Well, lots of stuff worked out really well. Okay. Did some upfront design work, looking at the existing calculations, make sure they're stateless, etc., etc. And I focused on the important problem to minimize risks in other areas. You know, this code, yeah, that's basically it. Focus on the problem and don't try to optimize the areas that don't need it, right? Test first development worked great, especially since we could reuse existing tests as a starting point for our parallel implementation. Refactoring was key to maintaining one's sanity moving towards a new design. So this is an example of where refactoring really pays off, you know, where we start by just changing it so that we're moving the code so that it can be used in a different way. And yet we don't want to break the existing code. I got to say the task parallel library worked flawlessly at what it was designed to do. And we just needed to approach the problem correctly to make it work.